Welcome to the presentation of our online course, Simulation, Scale-Up, and Optimization of Enzymatic Bioreactors. Through our online courses series, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and animal cell cultures processes. For more details, visit us at bioprocessengineeringonline.com. Enzymes are increasingly utilized in industrial processes due to their exceptional catalytic properties, including a broad spectrum of catalytic activities in both aqueous and non-aqueous environments. The ability to function efficiently under mild conditions of temperature, pressure, and pH, high chemo, regio, and enantio selectivity, enabling precise and selective transformations. Thanks to their unique properties, enzymes serve as valuable biocatalysts, enabling the synthesis of novel molecular architectures that are difficult or impossible to achieve through conventional chemical methods, supporting the development of more efficient and sustainable production processes with fewer reaction steps and reduced use of toxic or hazardous reagents. Industrial bioconversions make use of enzymes in a wide range of applications, including the synthesis of fine chemicals, active pharmaceutical ingredients, chiral intermediates, and bioactive cosmetic compounds, the production of food and beverages, the conversion of renewable resources into biofuels and bio-based chemicals. For bioprocess engineers, one of the key challenges is designing and scaling up enzymatic bioreactors that are both efficient and economically viable. This process typically begins with small-scale laboratory reactors and advances toward large-scale reactors capable of producing products at the kilogram to ton scale. During scale-up, enzymatic bioreactors must be carefully tailored to the specific requirements of the bioconversion, including reaction kinetics, substrate and product characteristics, and process conditions. Given the wide diversity of bioconversion reactions, a broad range of reactor technologies can be employed. Among the most common are reactors utilizing soluble enzymes, such as stirred tank reactors, cascades of stirred tanks, tubular reactors, and membrane bioreactors. In addition, various reactor technologies are available for immobilized enzymes, where enzymes are immobilized using adsorption, covalent bonding, reticulation, or entrapment techniques. Common configurations include stirred tank reactors and fixed bed reactors, both adapted to support immobilized enzyme biocatalysts. To design high-performance enzymatic bioreactors, engineers rely on the advances of bioprocess engineering. This scientific discipline provides a conceptual and methodological framework for the simulation, scale-up, and optimization of bioreactors. Its ultimate goal is to enable the most efficient and productive use of enzymes in biomanufacturing processes. To accelerate process development and scale-up, bioprocess engineering increasingly relies on knowledge-driven simulation models built on a deep understanding of key physicochemical and biological phenomena. These models act as digital twins, virtual representations of bioreactors, enabling in silico experimentation across a wide range of operating conditions. Typically developed using laboratory-scale experimental data, these models play a crucial role in optimizing operating modes and process parameters, ultimately supporting goals such as maximizing productivity or minimizing production costs. For those new to bioprocess engineering and enzymatic bioconversions, Bioprocess Engineering Online offers a short introductory course covering the technologies and engineering principles of enzymatic bioreactors. This course is an in-depth, advanced program focused on the application of digital methodologies in bioprocess engineering, specifically for the scale-up and optimization of enzymatic bioreactors. The course is structured into two key phases. One, model development from laboratory data. In this phase, you will learn how to apply fundamental bioprocess engineering principles to develop mechanistic simulation models based on laboratory-scale experiments. These models are tailored to the specific enzymes and bioconversion reactions in use, enabling you to capture and describe the key phenomena governing the biotransformation process. 2. Simulation-guided scale-up and optimization. Building upon your model, you will explore how to use simulation tools to guide the scale-up of the bioconversion process and optimize operational strategies. Special emphasis is placed on selecting appropriate bioreactor technologies and operating modes to enhance enzymatic efficiency, maximize process productivity, and minimize production costs. The central thread of the course is a case study focused on a starch saccharification bioconversion process, one of the most prominent industrial applications of enzyme biocatalysts. Starch hydrolysis represents the largest enzymatic biotransformation in industry, serving as a key step in the production of glucose from renewable resources. Industrial starch hydrolysis typically involves two enzymatic steps. One, liquefaction, catalyzed by alpha amylase, which breaks down starch into maltodextrin oligosaccharides. 2, saccharification, catalyzed by glucoamylase, which further hydrolyzes maltodextrins into individual glucose molecules. This course focuses specifically on the second step, starch saccharification, as the core case study, using it to demonstrate model development, scale-up, and optimization strategies in enzymatic bioprocess engineering. The course is structured into two parts, comprising a total of 8 sessions. Part 1, Bioconversion Kinetics and Simulation, contains 4 sessions. Principles of Enzyme Bioreactor Engineering, Kinetic Analysis of Bioconversion, Simulation Model of Soluble Enzyme Reactor, Simulation Model of Immobilized Enzyme Reactor. Part 2, Scaling Up and Optimizing Bioreactors, is made of 4 sessions. Batch bioreactor optimization, continuous stirred bioreactor optimization, continuous tubular bioreactor optimization, fixed bed bioreactor optimization. The 8 sessions can be taken independently. In the first part of the course, you will develop a knowledge-driven simulation model of bioconversions reactors. These models are built on a scientific understanding of the fundamental phenomena that govern bioconversion in bioreactors, including the enzymatic reaction, mass transfer, and fluid flow. This mechanistic approach allows you to simulate and predict bioconversion reactors under varying conditions. Session 1, Basic Principles of Enzymatic Reactors Engineering, is designed for learners new to bioprocess engineering. The session provides a solid foundation in the essential principles needed to design and model bioconversion reactors. You will be introduced to 4 core topics: kinetics of enzymatic reactions, mass transfer in bioreactors, mass balances applied to bioreactors, and residence time distribution in bioreactors. The first step in developing a bioreactor simulation model is to analyze the kinetics of the bioconversion reaction. Kinetic modeling of an enzyme-catalyzed reaction requires the characterization of 2 simultaneous processes: the catalytic transformation of substrate into product molecules, facilitated by the enzyme; the thermal denaturation of the enzyme, conceptualized as the conversion of active enzyme into its inactive form over time. Accurately describing both processes is essential for building a reliable and predictive simulation model of the bioconversion. In Session 2, you will analyze the kinetics of maltodextrin hydrolysis by the selected glucoamylase enzyme in a laboratory-scale batch bioreactor. To investigate the kinetics of the hydrolysis reaction, you will monitor the time-dependent concentration of glucose produced during the reaction. Using this data, you will determine the initial rates of maltodextrin hydrolysis at varying concentrations of maltodextrins, glucose as a potential inhibitor, and at different temperatures. Based on these results, you will establish the kinetic rate law for the reaction, expressing the reaction rate as a function of enzyme, substrate, product concentrations, and temperature. To investigate the kinetics of enzyme denaturation, you will measure the time-dependent decrease in active glucoamylase concentration during the reaction. From this, you will determine the rate of enzyme deactivation at different temperatures. Finally, you will derive the kinetic expression for glucoamylase denaturation as a function of enzyme concentration and temperature. In Session 3, you will learn how to build a simulation model of soluble enzyme bioreactors using the insights gained from the kinetic analysis. To construct the model, you will integrate the previously established kinetic laws for maltodextrin hydrolysis and glucoamylase denaturation with the instantaneous mass balances that govern bioreactor operation. These mass balances, applied to the substrate, product, and active enzyme, are based on the principle of mass conservation expressed as inlet rate plus or minus reaction rate equals outlet rate plus variation rate. This framework allows you to simulate the dynamic behavior of the bioreactor under various operating conditions. By combining the instantaneous mass balances with the kinetic laws of the bioconversion, you will derive the system of differential equations that describe the time evolution of maltodextrin, glucose, and active glucoamylase concentrations. You will then learn how to numerically solve the system of differential equations on a spreadsheet to simulate the time-dependent behavior of substrate, product, and active enzyme concentrations under specified bioreactor operating conditions. In Session 4, you will extend the simulation model to an immobilized enzyme reactor, where enzymes are fixed within porous spherical particles. In this system, beyond the previously modeled reaction kinetics and enzyme denaturation, the simulation must also account for an additional rate-limiting step: substrate transport from the surrounding medium to the immobilized enzyme. This transport process is governed by two key kinetic laws. Intraparticle diffusion describes the rate at which the substrate diffuses through the pores of the particle to reach the enzyme. External mass transfer describes the combined effect of diffusion and convection, transporting the substrate from the bulk solution to the particle surface, with convection driven by the flow of the surrounding medium. By combining the instantaneous substrate balance within the particle with the kinetic laws governing substrate transport and enzymatic reaction, you will determine the concentration profiles of maltodextrins both inside and outside the porous particles across varying immobilized glucoamylase concentrations. Based on these concentration profiles, you will calculate the overall maltodextrin conversion rate for each particle. You will also assess the impact of diffusional limitations on the bioconversion efficiency as a function of the immobilized enzyme concentration. The second part of the course covers the digital scale-up and optimization of enzymatic bioreactors. Building on the simulation models developed earlier, you will compare 4 bioreactor technologies and operational modes: batch reactor, continuous stirred tank reactor, continuous tubular reactor, and fixed bed reactor. For each configuration, you will optimize 2 key operational parameters: temperature and added enzyme concentration. More specifically, this case study aims to design a starch saccharification process using glucoamylase based on the following production specifications: 15,000 tons per year of processed maltodextrins, a liquefied starch solution with an initial 300 grams per liter maltodextrin concentration, and a conversion yield of 95% from maltodextrins to glucose. For each bioreactor technology investigated, you will determine the optimal operating temperature and enzyme concentration required to meet these production targets efficiently and cost-effectively. In this case study, the bioconversion cost serves as the primary optimization criterion. You will evaluate the total bioconversion cost in euros per kilogram processed substrate by integrating 3 main cost components: equipment, enzymes, and labor. The objective is to identify the optimal operating conditions that minimize overall bioconversion costs while maintaining high process efficiency. Session 5 focuses on the scale-up and optimization of the batch-stirred tank bioreactor. In the session, you will implement a step-by-step strategy for optimizing a batch-stirred tank bioreactor. Under given bioreactor operational conditions, you will use the simulation model to predict the time-dependent variations in maltodextrin and active enzyme concentrations. Based on the bioconversion kinetics, you will determine the key design and operational parameters of the bioreactor, including the batch duration required to achieve 95% substrate conversion, the required reactor volume, the annual enzyme consumption, the energy consumption. You will then calculate the corresponding bioconversion cost expressed in euros per kilogram of processed substrate. Finally, through simulation and analysis, you will identify the optimal operating temperature and enzyme concentration that result in the lowest overall bioconversion cost. Session 6 focuses on the scale-up and optimization of the continuous stirred tank reactor. In this configuration, after an initial batch phase, the substrate solution is continuously fed into the reactor along with the added enzyme, while the reacted medium is simultaneously withdrawn at the same flow rate. Due to thorough mixing, the reactor contents remain uniform in composition throughout. Following a transient phase, the reactor reaches a steady state, where substrate and product concentrations at the outlet remain constant. To meet the process requirement of 95% substrate conversion at steady state, the flow rate, and thus the residence time inside the reactor, is carefully adjusted. Session 7 covers the scale-up and optimization of the continuous tubular bioreactor. In this configuration, the substrate solution with added enzyme is continuously fed into a tube-shaped reactor, where the reaction takes place as the medium flows toward the outlet. Unlike stirred tank reactors, the composition of the medium is not uniform throughout the reactor. As the mixture progresses along the tube, substrate and active enzyme concentrations gradually decrease, while the product concentration increases. To accurately simulate these spatial concentration variations, the tubular reactor is modeled using its residence time distribution, which captures the flow and dispersion characteristics within the reactor. At a constant feed flow rate and controlled temperature, the system reaches steady-state concentrations at the outlet. To achieve the target of 95% substrate conversion, the flow rate, or the residence time within the reactor is precisely adjusted. In the 3 sessions 5, 6, and 7, you will conduct virtual experiments to assess the influence of the two main operational variables, temperature and added enzyme concentration, on the bioconversion kinetics, the batch or continuous bioreactor sizing, with a focus on determining the required reactor volume and enzyme consumption, and on the overall bioconversion cost. By systematically analyzing these factors, you will identify the optimal operating conditions, temperature and enzyme concentration, that minimize the cost per kilogram of processed substrate. Session 8 investigates the scale-up and optimization of the continuous fixed-bed bioreactor. In this reactor configuration, enzymes are immobilized within spherical porous particles, which are packed into a column-type reactor to form a fixed bed. The substrate solution is continuously fed into the column. As the medium flows through the fixed bed, substrate molecules diffuse into the porous particles, where they are enzymatically converted into product, which then diffuses back out into the flowing medium. Similar to the tubular reactor, the system reaches a steady state under constant flow and temperature conditions. To achieve the target 95% substrate conversion at the outlet, the flow rate or residence time in the reactor must be appropriately adjusted. In this session, the previously developed simulation model for immobilized enzyme bioconversion is applied to simulate the kinetics of the fixed-bed bioreactor at given temperature and immobilized enzyme concentration within the particles. You will perform virtual experiments to evaluate the influence of two key operational variables on the bioreactor sizing, particularly the required reactor volume, and the annual consumption of enzymes and particle carriers, and the bioconversion cost, including the additional cost of the carrier material. Finally, you will identify the optimal operating temperature and immobilized enzyme load that minimize the overall bioconversion cost for the fixed bed reactor. The starch saccharification case study concludes with a comprehensive comparison of the four investigated bioreactor technologies and operation modes. Under their respective optimal operating conditions, you will compare operational variables, optimal temperature and added enzyme concentration, reactor sizing parameters, residence time, reactor volume, and required glucoamylase enzyme quantity. Overall production cost, expressed per kilogram of processed maltodextrins. This final analysis provides clear insights into the most cost-effective bioreactor configuration for the starch saccharification process. The course resources include recorded slideshow presentations covering mass balances in bioreactors, kinetics of enzymatic reactions, mass transfer kinetics, residence time distribution in bioreactors. Throughout the course sessions, you will use spreadsheet templates with a green-red correction system to analyze the bioconversion kinetics to determine the cost of the bioconversion. You will also use spreadsheets to simulate the operations of batch, continuous, and packed bed bioreactors. The spreadsheets will allow you to visualize the impacts of operational variables and identify the optimal operation conditions of bioreactors. You have the flexibility to tailor this online course to your individual pace. Plan and structure the course according to your own schedule. Additionally, coordinate the interactions with your tutor through video meetings. For further information on the course, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com.